So this one just has the answer up here, but you can see it's really not that bad to figure these out once you get the hang of it. They look tricky, really tricky at first, but they're not too bad, right? So here we have, at least if we remember the fundamental theorem of calculus. All right, so here if we're taking I don't know why the word derivative isn't up here, because that's our ultimate goal. But so here they just split the integrals. But what we're doing here is we're then taking the derivative of that. I borrowed the problem, so I didn't have to type it. And it should have in front of all of these d dx. Somebody was really lazy. So there should be a d dx in front of all of those. So if we're taking the derivative of the integral, okay, and on this one, notice that it doesn't match, right? So notice that our limits don't match. Excuse me. There's not what I meant to say. They're not. There's not a constant. Sorry, that we don't have a constant here. So notice that we have a 2x and not a constant. So we do have to split that. Make this one x cubed. This one's 0. The lower one will be 0, and then make the upper limit 2x and the lower limit 0. Or excuse me, they've done 2 steps at once. So let me back this problem up so that you can see all the steps. All right. So step number 1 is you need to change that. So then you'd have the derivative. This would stay x cubed. This would be a 0. ln t dt. And then it would be plus. This one would be the 2x. That's the lower. If we split it at the 0, notice that the zeros match from top to bottom, because it's from x cubed to 0, 0 to 2x, and that's ln t dt. And then flip those, so it's x cubed 0 ln t dt minus, and now the 2x, because the variable has to be the upper limit of integration. All right, so now we've got the variables at the upper. Now we can plug in. However, we have to do a chain rule here. So it will be natural log of x cubed, but then times the derivative. The derivative of x cubed would be 3x squared. And then minus natural log 2x. But again, we have to do a chain rule. Derivative of 2x is 2. And that's where that answer comes from. So I figured, let me just break that down a little bit. Okay, make sense? I don't even know why I put a 1 up here. There's only one problem. Make sense? Okay. And it's that easy. All right, continuing with fundamental theorem of calculus. If f happens to be a positive function, then g of x can be interpreted as the area under the graph of f from a to x, where x can vary from a to b. Okay, so you can think of g as the area so far in our function. So here we have our curve, and this would represent the area on the interval there.
So g of x represents the integral?
Yes. Well, no, the other way around. Well, this one here is our derivative. Yeah, you're right. The integral, which would be the original function. All right, so if f is the function whose graph is shown in figure 2, and g of x is the integral from 0 to x, ft dt, we want to find the values of g of 0, g of 1, g of 2, g of 3, g of 4, and g of 5, and sketch a rough graph of g. So here we have graphed our derivative, right? We're integrating, so we have graphed there the derivative. So this lesson does, this part, it does break it down into step by step each page. So I can go over the steps with you. Okay, so we're given that g of 0 is 0, and notice the distance there from 0 to 0. This is just going to be 0. You can see it. All right, so now g of 1. Right, so Here we haven't gone anywhere, right? And so the distance from here to the same value is going to be 0. Okay? So now g of 1 is going to be the distance, the integral evaluated from 0 to 1. And this is just a little piece. That's the same function there. It's just a little piece of that function. And if we look at a little piece of that function, we have a triangle. So from g of 1 is the area under the curve from 0 to 1. We have a triangle. One side, the base there is 1. The height is 2. So half times 1 times 2 is 1. So that means g of 1 is 1. G of 2 is the value under the curve from 0 to 2. Hope you're seeing a trend here. So we're going to find the area under our curve. Notice on my notes here, they did it as a, looks like they're doing it as a triangle and then the rectangle. They could have done it as a trapezoid. However, we already know that from 0 to 1 was 1. So why calculate that out again, right? And from 1 to 2, it's a rectangle there. 1 times 2, it's 2. So together we have 1 plus 2, or 3. So that means g of 2 is 3. All right, so now we're doing g of 3. Okay? Well, now we got a curvy part here, which is messing us up. We know that g of 2, so from 0 to 2, it was 3. And so from 2 to 3, you have to estimate a little bit there. They estimated 1 1/3. So we have to do a little bit of estimating. And sometimes it happens. So it looks like this is an all the way filled in box. But if we take a little smidgy here and fill the box over here, let's get 1/3 is left, roughly. Well, 3/10, a little bit less than 1/3. So now we're up to 4.3. Okay, so now we have to start subtracting areas because for t greater than 3, we're negative, right? We're under the curve. All right, so moving along here, f of 4 would be g of 3, so what we got for 3, minus the area under the curve from 3 to 4. So again, a little bit of an estimation here. Looks like it's pretty much the same as what was above over here. Looks like it's about 1.3. And it would be minus because we're below the x-axis. So now we're up to 3. What's that? We're back to 3, I should say, right? So f of g of 4 is 3. And then g of 5, right? So now we're continuing along the curve. So we're going to go to 5. And again, we're going to be subtracting. So we know that from 0 to 4, right, we were at 3. And so from 4 to 5, it looks like that's the same. If this one was 1.3, this one looks like it's about 1.3 as well. So we're going to subtract another 1.3. So g of 5 is 1.7. Okay, now we could use these values to sketch the graph of g. Right? So notice that because f of t is positive for t greater or t less than 3, we kept on adding areas, right? So it kept increasing, right? So this one was, so maybe we should write everybody down so you can kind of see. So g of 0 was 0, and g of 1 was 1. G of 2 was 3. G of 3 was 4.3, right? G of 4 was 3, and then G of 5 was 1.7. All right, so notice that in our graph here, we have 0 graphed. Now, trying to have 0 graphed with on my smartboard. We have 1, 1. We have 2, 3. We have 3, 4.3. We have 4, 3 again. So notice it's going back down. And then we have, because it was negative, right? So from the t values greater than 3, we were negative. So notice the graph is going back down again. And then we have 1.7 here. And if we connect to those points in a nice smooth curve, we have a graph here. So what do you think that's the graph of?
The original function.
The original function. So now we could take the derivative, use the area under the curve to get the original function. And we can do that courtesy of fundamental theorem of calculus. And now we're back to our original function.
Minus
Is
the
it-
constant.
This is witchcraft.
What? Oh,
Right, so if we sketch the derivative of the function g as in the figure by estimating slopes of tangent, we get a graph like f. So now, if we were to take this, and remember when we did we're looking at the graphs of derivatives, if we were to graph the slopes at each of the points, we would get this graph, right? So here the graph looks like it's about, it's about 2 here. And it's about 2 and all the way, through 1. And then up here, we got a horizontal tangent there. So here we're curving. So notice that where we're curving, we'd have a straight line. Where we'd have a horizontal line where this is straight diagonal. So this would just be the slopes of this guy. So this guy here is the derivative. And this guy here was the original function. So by using slopes of a function, we can graph the derivative. By using areas under the curve of the derivative, we can graph the original function. And that's important to be able to do.
It all makes sense now. Everything is explained.
So to see why this generally might be true, might consider a continuous function of f with f of x greater than or equal to 0. So g of x is the integral from a to x of f of t dt, can be interpreted as the area under the graph of f from a to x. And we know that is our definite integral, is the area under the curve. It also gives us our original function.
So the area under the curve just represents a value or a point on the original function.
Yes, yes. So that's a good point. So what this area is, it's the total accumulated value. So as the value is increasing, the function's increasing. As the value starts to decrease when it goes under the curve, so long as it's above the curve, we keep adding value, the function's increasing. As soon as this goes below the curve, then we're taking away.
So that's how it describes it.
Yeah. So if we're thinking about a velocity curve, the area under the velocity graph is the distance. While it's positive, we're moving in the positive direction. When we have a negative area, negative velocity, we're moving in the negative direction. We're moving back again. And we'll see more of that in the next lesson, which is net change. Okay, so the two main concepts of calculus are integration and differentiation. The fundamental theorem of calculus says that these two concepts are essentially inverse to one another. The fundamental theorem states that if f has a continuous derivative on the interval a to b, then so this is the first part of our fundamental theorem of calculus. When we integrate and then evaluate, okay, that's going to give us the definite integral, and it's the area under the curve. So this form allows one to compute integrals by finding any derivatives. That means we don't have to always use limit of Riemann sums. The fundamental theorem of calculus says that integration undoes differentiation up to a constant, which is irrevocably lost when taking derivatives. Okay. So in a sense, the integral of the derivative of the function, the integral of the derivative is our original function again. Okay. So if this under here is the derivative of this guy over here, and we integrate it, we get back to the original function, and then we have to add the constant in because he gets lost.
Now, is it wrong if you don't write plus c? Because when I was learning calculus summer, they said if you don't write plus c, it's wrong. You have to represent that it is there.
It is wrong. It's and whenever it's the indefinite. It's not needed on the definite because the c's would cancel.
Okay.
So nobody bothers to write that. because you have a plus c and a minus c, and then we cancel one another out. And then the second part says that differentiation undoes integration in a sense that the derivative of the integral of a function is, back to your derivative again, right? So integration and differentiation are inverse processes. And those are the two parts of the fundamental theorem of calculus. It's actually a very big theorem. I've only really touched on it. And we'll look at it more as we're looking at some other things.
Wait, what's the fundamental theorem of arithmetic?
That every number can be broken down into a product of primes.
Okay.
Okay, suppose f is continuous on AB. So if g of x is equal to the integral from a to x of ft dt, then g prime of x equals f of x. Okay? In other words, the derivative of this one would give us this one here, this value here. Okay? Because integration undoes, gets back to the function. If we take the derivative, we differentiate, we get this guy. And then the second part, and then we had these reversed. We did, this is the first, so what it says 2 was for part 1, and what says 1 was part 2 for us, but who's part 1 and who's part 2 doesn't really matter. It gets flipped all the time. But the other part says that we can evaluate the definite integral by integrating and then evaluating, where f is any antiderivative of, big F is any antiderivative of little f. In other words, the derivative of f is f. Okay? So two big parts of the fundamental theorem of calculus are the relationship between the derivative and the integral and the original function, and the fact that we can find definite integrals by integrating and then evaluating.
Don't change it, please.
Sure.
That was the last box in our notes.
Yeah, I was gonna say, this is also on the notes, you could just read it here.
Do you not have, they're right in front of you, Russell.
It's right here.
They are literally
It's
right in front of
fine.
you.
And I didn't put this one in the notes, but this is one I thought we could do together.
The derivative of the integral.
So I'm going to pause the tape, and then we're going to do this one together.